Hello everyone. Today we are going to explore how AI see the world. Now, not just what it predict, but why it makes those predictions. This journey will introduce us to a powerful concept called saliency map. Myself, Dr. Amit Kumar Yadav, Associate Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana. What if AI could show us what it sees? The black box problem in AI. Imagine AI can tell a cat from a dog. Impressive. But how does it know? What features does it actually focus on? This is the black box problem. We see the output but not the region behind it. The AI gives us an answer but stays silent on why. In another word, we can say that AI models today are incredibly powerful but often mysterious. We call this the black box problem. We see the answer like this is a cat, but we don't see the reasoning behind it. AI where Waldo introducing saliency map tools that reveals what exactly means. What is saliency map? A heat map for AI. A specific image overlaid on the inputs, highlighting the most important region the model focused on. Bright is equal to important. Bright or warm color spots indicate pixel that strongly influence the AI prediction. Dark, it means less relevant. Cooler, darker area had little to no impact on the final decision. The AI largely ignored them. So we can say that in another word, a saliency map is essentially a heat map over an image. Bright areas shows what AI considered important. Dark areas shows what it ignored. It is like highlighting the AI's attention. Why do we need saliency map? First, debugging. Did AI learn the right features? For example, is it recognize a dog face or just its color? Trust. Before deploying AI in the real world, we need to verify it's making decision for the right reason. Understanding. Saliency map give researchers and developers a window into how the model form its predictions. In another word, we can say that why we require this saliency. First, debugging. Are we training the model correctly? Second, trust. Can we rely on its decisions? Third, understanding what pattern has it actually learned. Real world examples: Airbnb photo classifiers. What happens? An Airbnb photo classifier can achieve an impressive 91% accuracy, but for the wrong reason entirely. It was rated photo quality based on watermark in the corner, not the actual content of the room. How was it caught? Saliency map revealed that the AI attention was consistently drawn to a corner of image where watermark appear rather than lightning, composition or the room itself. In another word, we can say that take here fascinating example. An Airbnb model has 91% accuracy, but it was cheating. It focused on watermark, not room quality. Saliency map exposed these flaws instantly. This shows accuracy alone is not enough. The basic idea, vanilla gradient saliency. Before we explore advanced method, let's understand the foundational concept, gradient, and how they reveal which pixels matter most to an AI prediction. Feed an image into the model. Get a score. Compute the gradient of the score with respect to each picture. Visualize the result as a saliency. We can say that we input an image, get an prediction. The then compute gradient, which tells us how each pixel influences the results. Gradient, the slope of AI decisions. Pictures here a hill. Picture a hill. The gradient tell you which direction is the steepest uphill path at any point. In AI, gradient tells us if I nudge this pixel slightly, how much does the prediction change? A high positive gradient means that pixel is strongly focused toward its prediction. It's a key features. In another word, we can say that think of gradient like a slope on hill. They tells us if we change the picture slightly, how much the prediction change. Vanilla gradient saliency, the first step. The simplest saliency method uses the raw gradient of the model output scores with respect to each input pixels. Compute gradient, calculate how each pixels affect the prediction scores. It focus on positives. Keep only the gradient that increases the prediction. Build the map. Visualize pixel importance as a color overlay. The result, a basic important map that reveals which pixels the model relies on most. So we can say here the vanilla gradient method simply highlights pixel that pushes the pixel uh, prediction higher. It gives us first glimpse into models' attentions. Vanilla gradient in action. When the model classifies a cat, the vanilla gradient silently maps light up brightest around the cat face, ears, and eyes. The most distinguishing features. Less informative region like background or plan fur remains dark. The AI naturally ignored them. Even this simple method gives us meaningful first look at what the AI has learned to pay attention to. In another word, we can say that for a cat image, the model focus on the face, ears and eyes, background mostly ignored. Even a small method reveals meaningful patterns, making saliency map smoother and better. Vanilla gradient are a great starting point, but in practice they can be noisy and hard to interpret. The next generation of method clean things up. But there is just a problem with noise. The maps can be noisy, random pixels light up, making interpretations difficult. The problem noisy gradient map. What noisy means? Vanilla gradient maps often look spiky and pixelated. It means individual pixel light up seemingly at random, making patterns difficult to spot. This happens because gradients are sensitive to teeny irrelevant variation in the input, like random pixel fluctuation. What is the reason behind this problem? A noisy saliency map is like a blurry photograph. It technically shows the skin, but the important details get lost in the static. We need cleaner, more coherent map to extract meaningful insights from the models. Then smooth grad, adding a little blur strategically. By averaging across many slightly perturbed version of the same image. So smooth grad cancel out random noise and signal and giving us much cleaner and more interpretable saliency maps. So we can say here we add small noise to the image multiple times and average the result. This cancels out randomness and reveals the real signals. Noisy versus smooth gradient. See in the forest for the tree. Vanilla gradient is spiky, pixelated and hard to read. Individual pixel fire without a clear pattern. Noisy drowns out the signals. Smooth grade, smooth, coherent and much easier to interpret. So for comparisons, we can say here vanilla gradient look messy and unclear. Smoothie gradients give us clean, smooth, interpretable maps. Now we can actually see what matters. Advanced techniques, the most powerful salience method go deeper literally. They analyze specific layers inside the network provides, say, richer, more precise explanations. So GradCam work at deeper layers in the network instead of pixels. It highlights meaningful regions like entire object. This makes interpretation more easier. GradCam++, even more precise. GradCam limitations when multiple instances of the same object appear in an image, GradCam can blur them together into one large region. The GradCam++ fix. GradCam uses a weighted combinations of positive partial gradient, which make it more sensitive to individual objects. Result better localization of multiple objects simultaneously, with sharper and more accurate. Layer-wise relevance propagations. It is called as LRP. LRP takes a different approach. It starts from output and work backward. Distribution relevance to each pixel. Every part of the decision is accountable for. So we can say that the future of AI is not just powerful but explainable in healthcare, self-driving cars and fairness. Understanding decision is critical. Saliency map help us build AI we can trust. Understanding our model visualization techniques. What are visualization techniques in machine learning? Imagine a black box model which took data and split out prediction. But you are having no idea why. Visualization techniques help us peek inside the box. They reveal how a model makes its decision, turning individual logic into clear, interpretable visuals that anyone can understand. Why do we need to understand model? Build trust. Verify that prediction makes sense before acting on them. Fix error. Spot and correct unexpected model behavior early. Ensure fairness. make model more reliable and unbiased across, explain decisions, communicate model reasoning clear. In another word, we can say that why is this matter? First, trust. We need to know prediction makes sense. Second, debugging. We want to catch error early. Third, fairness. Our decision unbiased. And finally, communication can be explained results to others. Partial dependency plot PDPS, our first major visualization tool showing how individual features shape a model's prediction on average. What is partial dependency plot PDP? PDP answer a focused question: how does this one features affect the model prediction? What it does? It averages out the effect of all features in the datasets. It isolates the pure relationship between one features and the outcome. Think of it as hearing the average story of a single features. So we can say here a partial dependency plot answer a simple questions. How does one features affect the model prediction? It isolates the features and show its overall influence. How PDP works. The simple idea: pick features, vary value, predict output, plot the trend. Here the idea: we vary one features, keep other constant, and observe how prediction change. This gives us clean trend line, the average story of that features. PDP example: temperatures and bike rentals. Features: temperature in say degree centigrade. Prediction: number of bike rentals per day. PDP shows as temperature rise, bike rental generally increases, a clear positive trend. So we can say here in say features interaction, but reality is really that simple. Two features can interact like temperature and humidity. PDP shows can shows this interaction, revealing more complex patterns. What PDP tells us? With PDP, we learn direction of influence, strength of effect, interaction between features. It gives us a strong big pictures understanding. What it tells us: overall trend. See whether a features pushes prediction up, down, or stay flat as its value changes. Strength of effect. Determine if a feature has a strong or weak influence on the model's outputs. Features interaction. Two-way PDPs reveals how two features work together to shape predictions. PDPs, the big picture views. What PDP does best, they provide global understanding how each features affect the model on average. Great for high level insights and communication. However, there are certain limitations. PDP assumes features are independent, but in real features often correlate, which can sometimes make PDP misleading. Individual conditional expectation plot called as ICE plots. So ICE plot reveals the unique prediction story for single for every single data points. What is an ICE plot? An ICE plot is like a PDP but much more personal. Instead of one average line, it draws one line per data point. Each line tells the personal story of how features affect that specific samples. The results are rich savagity of lines revealing hidden variation in the model. In all ICE, lines look similar. The PDP tells the full stories, they diverge. There's importance variation to explore. So IC plot tells a personal story instead of one average line. We get one line for each data points. How IC plot works. The simple ideas. Pick features. Choose one features. Example temperature. Select point. Pick a single data point. Example days. Vary features. Change that features values for the point. Record predictions. Log how the model's predictions shift. Repeat for all. Do this for every point to build lines. In simple sentence, we can say that we pick a data point, vary one features, track prediction changes, repeat this for all data points, and we get full ICE plots. Examples, temperatures, and bike rentals. Here key insight, most day follows the trend, but some like rainy don't. IC reveals this exception that PDP completely hides. IC versus PDP. What's the difference? PDP, the average views. One smooth line representing the average effect across all data points. It is clear, simple, and great for communications, but can hide important variations. ICE the individual views many lines, one per data points, showing how the features affect each samples uniquely, reveals exceptions, outliers, and hidden subgroup the PDP might miss. The PDP is actually the average of all IC lines. They are deeply connected. When IC is more useful than PDP, features effect vary by group. When a features affects young customers differently than older one, IC line will visibly diverge for different subgroups. Investigating specific case when you need to understand why a particular prediction was made, not just the average behavior. Detecting hidden interactions. When two features interact, IC line will cross or fan out a visual warning that PDP smooth line is over similars. PDP and IC plot better together. So we can say here it is a powerful combination. We are using PDP to get high level stories, then use IC plot to pressure test it with individual details. PDP first understand the general trend. IC next check if every data points follow that trends. Together build deeper, more honest model understandings. Key takeaway partial dependency plot PDP shows average effect of one features on prediction. Great for global understanding and communicating trend clearly. IC plot shows the effect of features for each individual data points. Uncover hidden variations, subgroup and exception. Use both together. PDPs and IC plot complements each other's average trend plus individual stories for complete model understandings. Visualizing for understanding turns numbers into stories. PDPs and IC plot are powerful tools that makes even the most complex machine learning model interpretable. They transform abstract math into clear vision narratives, making it possible to question, trust, and improve your models with confidence. So, key takeaway, let's summarize. PTP shows the average trend, ICE shows individual trends. Together, they provide a powerful toolkits for understanding machine learning models. Visualization turns numbers into stories. It helps us question model, trust their decisions, and improve them confidence. So we can say here we can test PDP and IC plot on real data, compare them and always ask one question. Why did the model make these decisions? Thank you.